All right, problem of the day number 1. Let's go over the key for this. This is really similar to the lab we did with trans-stilbene, and you may recall in the post-lab it referred to a compound, or the trans-stilbene forming meso products. And so in this case I asked you to look at the same thing with butene. So let's do trans-butene at first. And I'm going to do kind of an odd view of trans-butene. I'm going to do a side-on view rather than an on-top view. So let's imagine looking side-on here. And we've got this set of p orbitals sticking straight up and down. These are the pi bond, right? So in an addition reaction, you can use either lobe of the p orbital to do that nucleophilic attack. So when we do our reaction, we actually get 2 different products. We could have attack by that top lobe and kick off our bromine, which would result in a bromonium ion where the Br is sticking straight up. And on the right-hand side, our H is a wedge and our CH3 is a dash. And we could have a CH3 that's a wedge here, and then that H is a dash. We can't forget that the bromine has a positive charge as well. Alternatively, we could have the bottom side attack and do this same reaction like we saw in class the other day. And if that bottom lobe attacks, we've got a bromine pointed down. Got a hydrogen that's a wedge here, a methyl group that's a dash, and over here our methyl group is a wedge, and our hydrogen's a dash. Sorry, let me clean this up a little bit. All right, now we can have our bromide react, and this bromide is going to do an SN2 style attack, so it needs to come in from the underneath side. It's not going to do a top face attack, and then it's going to ring open. The neat thing with this reaction is that you only get one product. Why do we only get one product? Does anybody have an idea? Yeah, because it's meso. So if we look at this compound, it's not immediately clear that it's a meso compound, but remember that sigma bonds can rotate. So if we rotate that internal carbon-carbon bond and stick that bromine straight up, we would have an internal plane of symmetry, and this would be meso. Oftentimes when people name meso compounds, they just simply refer to them as meso instead of giving the R and S designation. You could write R and S, or 2R and 3S, or 2S and 3R. It doesn't really matter. But if you want to, you can write meso 2,3-dibromo butane. Does that make sense? So even if you try to draw all of the possible products, you're just drawing the same product. You're not drawing molecules that are any different.
Why are there 2? Can we do only one?
That's a good question. So for the bromonium ion intermediate, are those identical? What do you guys think? No. The intermediates we have drawn are actually enantiomers. There's no internal plane of symmetry in them, so we can't refer to them as meso. So in that case, we do want to draw both intermediates and then draw one product, since there's only one possible product, regardless of the intermediate you use.
So we have to draw 2 lines then?
I'll be flexible. Oftentimes what students do just to save time is they'll write plus EN, and that just means plus enantiomer, and they'll only include one intermediate.
Okay.
Yep. All right, for the cis version, I'm going to try to speed this up a little. We can have our cis attack this bromine, and again, this can do a top side attack or bottom side. So our bromine can stick straight up, and And we can have both methyl groups on the same side, so I'll show those both as wedges. And we could have one where the bromine is underneath. And we've got two wedges there. Now we have to take into account two different distinct reaction pathways. The first one could have the bromine attack from either face and ring open it. So now we've got Br, Br. The methyl group is still a wedge. The methyl group is still a wedge. Or we could have it attack here and ring open it. Oops. And then we've also got a wedge and a wedge. So let's go through and try to name these. So if we look at the first one on the left, bromine would be highest priority. This group would be second highest priority. This group would be third highest priority. So what's the designation for that stereocenter? It'd be R. Okay, and then if we look at this stereocenter over here, bromine would be 1, 2, and then 3. So what would the stereocenter be? R. Okay, so if we try to name this, we could name this 2R, 3R, 2,3 dibromo butane. And then we can do the same thing for the molecule on the left. Oop. So let's try to designate the R and S designations. For this stereocenter, we would go 1, 2, 3. So would that be R, S? S. And then the one over here, we could go 1, 2, 3. So what would that be? S. So we could write 3S, or sorry, 2S, 3S. Shoot. 2S, 3S, 2, 3 dibromo butane. What's the relationship between these two? Enantiomers. We flipped all of the stereocenters. There's no internal plane of symmetry. So in this case, we would get a racemic mixture of products. This is one common theme you'll see in addition reactions. You have to watch out for stereoisomers. You might end up with a pair of enantiomers. You might end up with a pair of diastereomers. But try to draw out all possible reaction pathways. Some of them may be identical. Try to match up the identical ones and try to spot sets of enantiomers if you form them. Are there any questions?
Is there like a pneumatic way to remember, like when you break open the chain, what ends up where, what ends up as a dash, and what ends up as a wedge?
I normally tell people try to draw the full mechanism with dashes and wedges. If you want some practice, feel free to stop by my office or go through some of the book problems. A lot of it just requires repetitive practice to start seeing the trends in it. Yeah. All right, so let's go back to our halogenation section from chapter 9. And this was where we kind of ended yesterday and closely related to our pod. We said the first step is always going to be a nucleophile, specifically your pi bond, attacking your halogen. And then you form a bromonium ion, and your bromine will attack and ring open it. Why didn't I show two different enantiomers for the top intermediate? They're identical. So I could have drawn it 100 times, it wouldn't have made a difference. But if there are sets of enantiomers, you should try to draw both. In this case, it's also important to remember that the bromines add anti to one another, so there is specific stereochemistry as a result. And then we went through an example problem, and like I said on the problem of the day, you always have to watch out for mixtures of enantiomers. The next reaction we're going to do is closely related to halogenation, and it's called the Halohydrin reaction. So if we look at the Halohydrin reaction, it's very, very similar. We're going to take an alkene, and we're going to react this with bromine, so Br2. But this time we're going to react it with bromine that's in water. So the first step in this reaction is our pi bond will attack our bromine, kick off bromide. And again, we're going to form our bromonium ion, where one methyl group is sticking down towards us, the other one's sticking down away from us. Let's clean this up a little. There we go. And our bromine has a positive charge, and we've got Br minus. However, in this reaction, we've got water. Bromine or bromide can be a nucleophile, but water can also be a nucleophile. If we're running this in an ocean of water, what do you think is going to win as the nucleophile? The water, just simply because there's more of it. So in this case, the water will outcompete the bromide. It will do a backside attack and then ring open. So now we've got water that was added in, anti to our bromine. Our methyl groups are still dangling off of there, so I'll try to show the stereochemistry. There we go. And then what do you think the last step is going to be? Deprotonation. So oftentimes in these reactions you have deprotonation steps at the very end. So another equivalent of water could come, grab a proton off, and before you know it, you've not only added a halogen, but you've added an alcohol across that double bond. So let's make a couple of points here. The first point that I wanted to bring up was that we're still doing anti-addition. And the second key point is that water, or H2O, outcompetes Br minus as a nucleophile. It looks really, really similar to that last reaction that we saw, right? The halogenation reaction. The only difference is instead of having two bromines add, you only have one, and the second equivalent's an OH.
So is H2O a better nucleophile than Br minus, or just because of it's faster? Because it's like.
That's kind of getting into a tricky question. It's more that there's so much water around that it's just outcompeting the bromide that's around. You may observe a small amount of halogenation, though.
Okay.
Yep. All right, so now let's do another example of this, but this time we're going to look at regiochemistry and stereochemistry. So this time I'm going to choose an alkene that's not symmetrical anymore, or at least doesn't have those other two methyl groups.
Can you move on a little bit? Yeah.
There we go. And we're going to react this with bromine and water. All right. So now we've got to draw our intermediate, which again is going to be a bromonium ion. So is it okay if I scroll up?
Yep.
All right. And this pi bond is going to attack the bromine, kick off our bromide. And we've got this bromonium ion. Do we have to worry about an enantiomer here? What do you guys think? What do you think? No, Sarah?
Because the two substituents are the same, so it doesn't matter if they're change.
Exactly. If the bromine attacked from the bottom lobe, it would result in the exact same intermediate. So in this case, we don't have to worry about drawing two different intermediates. We only have one bromonium ion. Now, the tricky question is, if we have water around in solution, which carbon is the water going to attack? This brings in a debate. So now, let's think about this for a second. And I'm going to break this into two separate reactions. I'm going to have one listed in green that attacks the more substituted side. So in this case, I'm going to show this attacking underneath here, and we'll open it up. All right, so now let's draw the transition state for this. Now the bromine's got a partial positive because it's slowly gaining those electrons. We're breaking this bond, so we'll show that as a dash. We still have this methyl group that's dash. We've got this methyl group that's a wedge. And we've got this water group approaching from the bottom that's slowly gaining a partial positive charge. And if we think about it, this carbon right there is going through a highly polarized transition state. Let's do the same thing for the other side. And let's have the water attack this position and ring open it that way. Same sort of thing. But this time the bond on the right is breaking. And our water is approaching from underneath it. And we've got this Br with the delta positive. This oxygen's got a delta positive. We've got some methyl groups over here. And we've got a transition state that looks like this.
Didn't you say yesterday that it will attack the one posterior center?
What was that?
Didn't you say yesterday that it's going to attack the one posterior center?
It's going to attack the more substituted position, but let's try to rationalize why. Why do you think this carbon right here is more stable? The one on the left that I've got the arrow pointing to. Why would that carbon be more stable than this carbon over here on the right? Because it's more substituted, right? If we're going through a highly polarized transition state, it's much, much more stable when you have more substituents coming off of it. It's the same logic as carbocation stability, right? Tertiary is more stable than secondary, and that's more stable than primary. So in this case, this is going to be our more stable transition state. So if we know that, what do you think our product's going to look like? So let's go back up to our question mark up here, and let's try to fill that in with the appropriate product on the right. Will the bromine be on the left or the right? It'll be on the right. Our OH will be down here, and it will be anti, so it needs to be in the same plane but on opposite sides. We'll have a methyl group sticking up here, another methyl group sticking back there, and there we go. The reason we don't observe this one is because that would require going through a transition state that is significantly less stable. So anti-addition, and your alcohol is always going to end up on the more substituted side of your alkene. So let's even highlight it and make a point of that. Your OH will end up on the more substituted side of your alkene.
So the more stable one, the more.
In this case, we're not using Markovnikov or anti-Markovnikov terminology. We use Markovnikov and anti-Markovnikov when we're adding in a hydrogen and something else, but in this case, we're adding in two non-hydrogen groups, so we don't use that terminology anymore. That's a good question, though. Yep.
So would you use mercury acid for this case?
No, in this case, you just use bromine and water.
What if you wanted to do with the rearrangement and just go straight to like 1.5?
In this case, because we're going through a bromonium ion and not a true carbocation, we don't undergo rearrangement at all. We only go through that bromonium ion intermediate.
So the other ones you said you could use chlorine in the same fashion. Is this true with the water as well?
With the Halohydrin reaction, I've never heard of it being done with chlorine. Yeah. This is usually done with bromine. It's kind of a neat reaction to run. So you take basically a beaker of water, you drop in bromine. Bromine's ultra dense. It sinks to the bottom, and then the water turns kind of pink. And then you just take the water itself and add that into your reaction mixture. So chlorine, because it's a gas, doesn't dissolve super well into water, and I've never heard of anybody doing it that way. Yep. All right, so we're going to change gears away from the halogens and go more towards alcohols again. So let's cover a new reaction. I know you guys are giving me that look of like, are you serious? More reactions? With that being said, one thing I really, really recommend this term is reading ahead in your book and trying to dedicate time every night to review material. If you leave it until the end of the week, it's going to be overwhelming to deal with. So try to do a little bit every day and try to read ahead. The next reaction we're doing is anti-dihydroxylation. So let's take a look at an example of a dihydroxylation reaction. We'll take an alkene like cyclohexene, and we're going to use a new reagent, one we haven't seen before, called MCPBA. It's alphabet soup. So MCPBA, let's define it. It stands for meta-chloro peroxy benzoic acid. It's a mouthful, so most chemists just refer to it as MCPBA. And the M in this case is lowercase, the C, P, B, and A are all uppercase. And so let's draw this out. It's got a benzene ring in it. It's got a chlorine coming off of the benzene. And then it's got a peroxy group on it. Does anybody know what peroxy means?
2O.
Yeah, 2 O's. So it's like a carboxylic acid. However, it's got this oxygen-oxygen single bond in it. So it's a peroxide. Okay? So we can use this as a unique reagent. We're going to see this a lot more when we cover epoxides. And then in the second step, we're going to add in a little bit of acid. So we'll just indicate acid by H+ in brackets. And we're going to run this in water. By doing this, we're able to add 2 different alcohols across our double bond. But the alcohols are going to add on opposite faces of our double bonds. So in this case, they're going to be, anti to one another. So if you look at it flat down that cycloalkane, you'll notice that they're on opposite sides, and we end up with anti-hydroxyl groups coming off.
Why do you have to change?
So we'll go over the mechanism in a little bit more detail, but I just wanted to show you guys the outcome of this reaction before we go through the mechanism. The other thing we have to consider is the potential for forming an enantiomer. So in this case, do you guys think there could be an enantiomer? Let's try to draw it and see if they're identical. So if we tried to draw the enantiomer, the top one would be switched and the bottom one would be switched. Are these the same or are they different?
Same.
Are they? They're different. So if you take this one on the right and you try to flip it over and superimpose it on the other one, it will not overlay perfectly. So in this case, you're going to get a set of enantiomers. Now you guys understand why I was trying to drill this into your heads last term. Hopefully it didn't all fall out over break. So let's talk a little bit about the mechanism for this. Scroll up or down. The one nice thing is this is one of the mechanisms we're not going to cover in exhaustive detail, but I do want you to see the intermediate. Is it okay if I scroll down? All right, so let's take a look at the brief mechanism. We're not going to go through this mechanism in a whole lot of detail. We've got our alkene, and we're going to react this with MCPBA. And then the cool thing is we get an intermediate that looks really unstable, but isn't. It's got an oxygen in this three-membered ring. And these are called epoxides. And this is a really important intermediate in organic chemistry, and we're going to have a whole section in our alcohol chapter dedicated to epoxides, or sorry, our ether chapter. The next step of this reaction involves protonation of your epoxide. So your oxygen can come grab a proton. Yep. Yes. In this case, why am I not drawing an enantiomer? Yeah, it's the same. If I tried to draw the enantiomer of that epoxide, I'd just be drawing the same molecule. So there's no need to draw a different enantiomer. There are some cases, though, where you do have to consider the fact that there might be an enantiomer. All right, so now we've protonated our epoxide. That makes this epoxide very, very unstable. You can imagine that oxygen doesn't like being in a three-membered ring, and it doesn't want a positive charge. So the next step involves water attacking. And in this case, the water can attack from either face. It could attack from this bottom side and ring open it. So let's draw that product. When it does that, the OH ends up as a wedge on top, and that water must attack from that underneath side, just like we saw with the bromination. And we end up with that water added in as a dash. Do you think there's a potential of forming an enantiomer? Yeah, it could have added from that top face as well. So just to save some time, I'm going to write plus En instead of drawing out the opposite enantiomer. And we've got one last step. What do you think the last step's going to be? Yeah, just deprotonation.
What is it?
En stands for enantiomer. So if you don't want to draw out the opposite enantiomer, you can just write plus En, and it will save you a little bit of time, and I'll know what you're talking about.
Is it attacking the H?
Yes, so water is taking the extra proton off of that protonated alcohol, and it's going to neutralize it. And we regenerate our acid catalyst, which is why we show that H plus in brackets. We need less than a stoichiometric amount for this to occur. Yep.
All the examples that I've seen for this have some kind of, the epoxide is always a ring.
Mm-hmm.
What's the defining characteristic of the epoxide? Is it the grid with the oxygen?
Yeah, an epoxide is a three-membered ring with an oxygen in it.
Okay, so you could have something that wasn't like a cyclohexane with an epoxy.
Yes, this will occur with any sort of alkene, whether or not it's in a ring system or not.
Okay.
Oftentimes, too, you may hear people call it oxirane. That's another term for describing an epoxide. I'm fine with you guys using either, but most of the time in the Klein textbook, he refers to it as an epoxide. Yep.
When that water does detach from maybe the top or the bottom, does the OH that becomes a wedge on top, does that change at all?
Yeah, so if you imagine, hypothetically, this could attack from the top and then open it this way, right? Which would mean that this alcohol down, this alcohol down on the bottom would end up as a wedge, not a dash, if it attacked from that top face. So that would be your opposite enantiomer that could form. So in this case, you'll get two different products out, and it will be a racemic mixture that you're forming. Does that make sense? It's tricky to spot whether or not you're getting an enantiomer, so my suggestion for the time being is draw out all possible outcomes for the reaction, and then try to identify whether or not you're drawing the identical set of molecules or sets of enantiomers or sets of diastereomers. It's always better to play it safe at first. The other neat thing with this reaction is if we look at this, I'm using water right there. This will work with any sort of nucleophile. We'll see this a lot more when we cover the chapter on epoxides, but the key take-home message is you can use almost any nucleophile you want to ring open an epoxide, especially when it's been protonated. So let's make a little note of that. We'll also work with other nucleophiles.
We're talking about water right now.
What's that?
We're talking about water.
Yeah, the water could be any other nucleophile. So for example, you could use an alcohol, you could use a thiol, you could use anything with a lone pair really, and it will add in. All right, we've got one other reaction that's closely related to this. And instead of it being anti-dihydroxylation, we'll do Syn-dihydroxylation.
Does that mean that they're the same side and the other one's
Yes. So let's take a look at Syn-dihydroxylation. So we'll use that same cyclohexane example. And we'll use osmium tetroxide, so OSO4. Not the greatest reagent to use. It'll make you go blind if you get it in your eyes. No, we're not going to do this in the lab. And we need to follow this up with a reduction. And when you do this, which one? O4. So OSO4. Yeah. When you do this, you'll get a diol. But this time the alcohols will be on the exact same face. For this example, do we have to worry about an enantiomer? Why not? It's a meso compound, right? So if we tried to draw the enantiomer of this, it'd be the exact same compound. But in this case, we've got syn addition of alcohols across our double bond. Let's take a look at the intermediate for this reaction. I'm not going to require you to know the full mechanism because it's very tedious. But it goes through an organometallic intermediate where we have cyclohexene, and then we've got this osmium tetroxide down here. And the pi bond from the alkene will actually attack the oxygen coming off of the osmium tetroxide. And then the pi bond down here will attack the other end of your alkene. So now if we look at our intermediate, we've got two oxygens on the same side bound to osmium. And this osmium also has a lone pair on it. And then in the next step, we want to reduce off the osmium. And there's a handful of reducing agents you can use. Oftentimes in your book, you'll see, I think they use NMO, but I normally use sodium bisulfate. So NaH, or sodium bisulfite, excuse me, NaHSO3, and water. And in this step, we just cleave off that osmium, and we end up with our diol product, where our alcohols are on the same side. That's the extent to which I want you to know this mechanism. You don't need to know all of the rearrangement type stuff going on with the osmium or the inorganic chemistry that's occurring. Does that make sense? Yep.
This may be kind of a silly question, but can the osmium make bonds that were like trans instead of cis bonds with the
So with the alcohols on the opposite side?
like yeah, one on one side and one on the other?
No, sterically, it's too far to reach for that to occur. So it will only occur on the same side. That's a good question. Which is why this exclusively leads to Syn-dihydroxylation.
Is it OS or oxygen and sulfide?
It's OS for osmium. So it's not oxygen and sulfur, it's OS for osmium. There's also an alternate route. Technique. But I just wanted to show you guys this. It's not one I recommend using for synthesis problems because it's very, very excessive. You can use your cyclohexene and potassium permanganate. Whoops. So KMnO4. And then you use sodium hydroxide and you run this cold. And this will also give you your Syn-diol. The reason people don't use this method very often is potassium permanganate is a really, really, really strong oxidant. If you have other functional groups in your molecule, it will oxidize those functional groups as well. So it's a bit of overkill for most of your reactions that you're going to see. Most people, and most of the time in the Klein textbook, you'll see the osmium tetroxide mechanism. But I did want to show you this in case you see it in your textbook and you wonder, what the heck is KMnO4? It's going to do the Syn-dihydroxylation reaction. Make sense? All right, one last reaction today, and then tomorrow is going to be a review day for Chapter 9. We're not going to go on to alkynes yet, but make sure that you do your homework over the weekend. Next one. We're going to take cyclohexene again, and this time we're going to react it with O3, which is ozone. So this reaction is called ozonolysis. What does lysis mean as a suffix? Break. So we're using ozone to break a double bond. And the second step of this reaction is going to involve using something called DMS. That's dimethyl sulfide. Or you'll commonly see zinc and water used. Just like the last reaction we saw with osmium tetroxide, the first step is an oxidation, second step is a reduction.
Is that a ZN2 or is that comma?
It's a ZN comma. Sorry. And when we do this, we're going to cut this double bond. And we're basically going to replace that double bond with a carbon-oxygen double bond. So imagine this double bond just got cut. So can you guys see where that red dashed line was? That's where that carbon-carbon double bond used to be. We're cutting open that carbon-carbon double bond and inserting two oxygens in the middle. So what do we call this new functional group we formed? It's a double bond to an oxygen. There's a hydrogen coming off the carbonyl. Not a ketone. Starts with an A. Aldehyde. Aldehyde. Come on, guys. Aldehyde. This looks pretty weird to draw it this way, so oftentimes you'll just see it drawn out as a linear fashion. 1, 2, 3, 4, 5, 6. This is the exact same molecule. So ozonolysis is used to cut double bonds. And turns alkenes into ketones or aldehydes.
So what happens with the third oxygen?
It becomes waste, and if you go in the textbook, you'll actually see the full mechanism. I'm not going to require you guys to know the full mechanism because it's very, very steppy. So it just becomes waste. And you don't need to know the mechanism. I know it doesn't feel like I'm trying to simplify this for you guys, but I am. I don't want to overwhelm you guys with knowing a lot of the really, really steppy mechanisms. So the mechanisms I discuss in lecture, I want you to know them in so much as what we've covered in class. You don't need to know every single little detail from the book. So let's take a look at some examples of this and try to anticipate what the products would be. Oh. So let's take this alkene. And first step, we're going to react this with ozone. Second step, we're going to react it with zinc, water. Let's try to anticipate the product or products that we would get out of this. So let's use our red ozone scissors. We're going to cleave that double bond. Are we going to form a ketone or an aldehyde? So let's imagine cleaving this. Oh. We would have one oxygen there, one oxygen there. Are these ketones or aldehydes? Ketones.
Do we have to draw two ketones or just one?
That's my next question. Are these the same or different? Same. They're the same. So in this case, we get two identical ketones. There are some situations where you might get two non-identical ketones or aldehydes out of the reaction. So always watch out for that. Try to draw both and determine whether or not what you're getting is identical or not. All right, you guys want another one? This will be the last one of the day. All right, next one. We'll do ozonolysis for this reaction. And this time we're going to use DMS. Yeah. Raise your hand if you think you got this one already. All right, I'll give you guys another minute. This one's a little trickier. I'll give you guys a hint to get you started if you're stuck. We're going to cleave both alkenes. All right, so let's draw our products. We'd have one alkene where it looks like this, and then another one where it looks like that.
Do we have to draw it underneath each other?
You can draw it however you want, but let's just pause for a second. Are these the same, different?
Same.
They're the same. So we don't have to draw it twice if we want. We can just write, we're going to get this out of there. And is it a ketone or an aldehyde?
Ketone.
It's a ketone. So in this case, we'll get a ketone as our product. Yep.
So you know how you had one on the, you had two of those.
Yeah.
How did you have 4 oxygens if there's only 3?
So it's O3 and it's a gas. It's usually used in excess, so you're flooding the alkene with ozone gas.
Okay.
Yeah. One side note, too, that I think is pretty interesting is how many of you guys have noticed in labs some of the hoses, when they get old, have cracks in them and they get really brittle? Same thing's true with tires at home, right? If you've got an old wheelbarrow that's been sitting out in your backyard for a few years, the rubber starts to crack in it. That's an ozonolysis reaction. Rubber has a bunch of alkene double bonds in it, and the trace amount of ozone in our atmosphere will actually react with those double bonds, cleave them, and then weaken the rubber over time. That's why rubber has a limited lifespan. Yep.
So when you're giving us a problem like this, is it for us to assume that the ozone is in excess?
Yes, always assume the ozone's in excess for these problems.
So like the rubber on the car, it kind of like pops out.
Yeah, so old cars, they have to have their tires replaced because the rubber becomes quite brittle due to ozonolysis reactions. Yep.
If that's ozonolysis,
There's trace amounts of ozone in our atmosphere. So if you've heard of the ozone layer, we have some of it in our atmosphere.
so it's just concentration.
Yeah. All right, good luck with the problem of the day. It involves multiple steps. Try to work together on it.